Hello guys. So we're still on the topic of number base and we have some questions here under conversion. It said we should convert the following: 10110 base 2 to base 10, 457 base 8 to base 10. Then we have another one here which we might do, or we might take it as an assignment: 14b3 base 16 to convert it to base 10. So we should take note of the way I call these numbers out. This one, for example, should not be called, let me just highlight it. This one, 457 base 8, should not be called 457. And this is 10110 base 2. So we call the digits separately. So the reason is because we are not, if we say 456, for example, it means we are kind of calling it the way we call numbers in our base 10 system, and this is not a base 10 system, this is a base 8 system. So to indicate the base, the number or the base number is written as a subscript, very small in the front. So the same way we write 16 like this. Good. So how do we convert? The first thing I have to make sure we understand is, for those of us that watched the previous video, we have learned that number one, we deal with the decimal system. Is the most common system that we work with in our day-to-day life, and that's how we write numbers, that's how we communicate and record. And we use a system called positional notation. Let me just write that. We use positional notation to write numbers, to count numbers in general. And we said the positional notation makes it easier for us to write numbers because we can work with less glyphs or less symbols. So we're no longer dealing with the Roman, like they're doing what the Romans were doing, that they will be drawing different glyphs. Not just the Romans, other kingdoms in ancient times, the early men in general, they will draw different symbols, plenty, hundreds, just to represent different numbers. So but as the world is increasing, the recent data shows that we have over 8 billion people in the world today. So just imagine having even up to 1,000 symbols to put in your head to represent numbers. It's kind of outrageous. So, and another thing we learned from the previous video is that the positional notation that we use is different from the positional notation that the Romans use. If you remember your Roman numerals, there's sometimes when you do subtraction, there's sometimes when you add, depending on the position. If the lower number is on the left side of the bigger number, you subtract, and if the lower number is on the right side of the bigger number, you add. So but in our own positional notation, there's a difference. The numbers are in the position, or the values are increasing from right to left as you go. So as you go from right to left, the values are increasing. So I'm going to explain that in a short while. Then we also learned that there are several bases apart from our base 10 system. There is base 2 system, as we can see here, and the base 2 system, all bases have their usefulness. That's another thing we should know, because some people will be of the opinion that what's the point of actually making different bases? Are we even using them? Yes. Computer programmers use base 2 system, they also use base 8 system, they also use base 16 system, as we can see here, depending on what they want to program. But the most common that computer programmers use is the base 2 system. It's simpler for them to work with. Why? Because they have only two glyphs, which is 0, 0 and 1. And the way computer is programmed is so that it can just give input and output. It makes decisions that are mainly yes or no decision and on and off decisions, so it's easier for them to work with. So the mathematical language that a computer is programmed with is a base 2 system. So let us just remember that. So I was explaining something about the way our positional notation differs from the Roman numeral positional notation. So let me just explain that further. Let us say, for example, we have, for example, we have 500, or let me just say 545 in decimal. We already know that our decimal system is representing our base 10 system. So the value of this number, the value of these three numbers are different. So if we want to write it out in what we call expanded form, we say that the first 5 is representing 500, the second 4 is representing 40, and the third 5 is representing 5. So we know this because in our primary school days, we just say unit tens hundred. This is the way we usually write it then, so that we'll not forget. In fact, we'll keep this like unit 10, 100,000, 10,000, and like that. So, but if we look at this now, that's why we now say this is 545. When we add the three of them together, we get the value of the entire number. So you can understand what I'm saying now, that the values of these numbers increase from right to left. As you can see, I've put an arrow to illustrate what I'm saying. The from the right end here, or the far end to the right, the first 5 here, which I'm referring to this one, is having the lowest value, just units, that is 5. But at the far end to the on the far end to the left, that's going like this, where the arrow is facing, the last 5 we're having is having the highest value, which is 500, as we can see. So if there was another number, let's assume it was something like 1545. So the comma here, we used to using the comma because it also helps us to arrange numbers in their respective positions. This number 1 here will have even a more higher value compared to 5. It's going to be 1000. So my aim is not to go back to nursery school here. I'm trying to explain something. Okay, let me switch back colors. Good. So there is something else I want to explain, because using this positional notation, understanding the concept will actually make it very easier for us to solve the questions here very easy, like very easily. Because the positions here, these numbers up here, we can observe something, that there is a relationship between these tens, this hundred, even the thousands. I believe we use th to represent thousands. One thing I want us to take note of before I explain one important concept, then we'll solve our question, is that we don't we create placeholders or positions. This can also be called placeholders. That is our 100 tens unit. It can also be called placeholder. That's why we can also call this a place value system of writing numbers if we don't wish to use positional notation. We can only create a placeholder when we need it. If we don't need that particular placeholder, we don't create it. So keep that concept in your head. We can only create a position or a placeholder if we need it. This is what I'm saying. Let's assume we start with a unit. I will start with the base 10 system to explain. I start with my units, cool. And my unit have how many leaves? It has 10 leaves in our base 10 system. So I say 1, I say 2, I say 3, I say 4, 5, 6, 7, 8, and 9, and 0, of course. 0, but I'll just bend 0 here now, because 0 is representing no number. It's a placeholder that represents nothingness. So, but it's part of the glyphs. It's part of the glyph for all bases. So, but let's just keep it on one side. We'll use it when we need it. So let's assume I'm working with this base 10 system now with 10 glyphs or 10 symbols, 10 digits, and we are using it to count or record the number of people living in my community. And there are 9 people living in my community until one new member joins the community, and the community becomes 10. I know there are 10, but how do I write it? You can see that there is no other way for me to indicate that that there's an increment or there's an increase in the population. If, let's say, for example, there was an apple and or a ball, and we said anytime we are counting or recording 10 people, we are going to use that ball. It's a unique glyph to represent 10. You can see that makes sense. We would have just put the ball under here and say that is representing my ball. Anybody that see the ball will know that there are now 10 people. But there is nothing like that. We don't have a ball representing 10. So what do we do? The solution now is to create a placeholder for 10 and say we have another place called tens place, like that. So this is tens. And under that tens, because one new member has joined, we will now write 1 there. And if we write 1 there, it's because it's under tens place, it means that 1 is representing 110. For our unit cannot be 1 again. Let me reduce the size of this. Our unit is going to be 0 in this. So now will now bring our 0. Our unit will now be 0. So 1 tens and 0 units is going to give us what? It's going to give us 10. That 10 people are in my community. So if we keep counting like that, if this is 2, we know that is 20 people, or 2 tens. If this is 3, that is 3 tens or 30 people. And you count until you get to 9. 9 under tens indicates what? 9 tens, which is 90 people. And let's assume that the population of my community is increasing, and I have 9 tens and I have 9 units, which if we combine, we call it 99. 99 people in my community. Let's assume one more person joins. If one more person joins, there are 100 people in my community. But how do I write 100? If there was, let's say, a banana, and that banana was representing, there was a banana, and the banana was representing 100, then we could have just put a banana there. And everybody, when they see banana, you know, oh, they are cool, they are 100 people. So it's all about something that is accepted. And the positionals, we don't need a banana, we don't need a leaf. What we just need to do is to create another placeholder for 100, for 100's place, so that anywhere we see anywhere we have 100, instead of drawing different leaves, we want to avoid that stress. Our 10 leaves that we use is already okay. What do? We'll just write 1 here under 100. If you write 1 here, I'm going to clean this. Instead of 1 under tens, we are going to replace that with 0 as well. We'll replace that with 0. And what that implies is we have 100s, 0 tens, 0 units. So you see where 0 comes in to represent that there is nothing under that placeholder. So this is 100 people. That's 100 people. That's 100. As simple as that. So this is, I'm just trying to explain what I said, that you can only create a placeholder or a place or a position when you need it. Look at the base 2 system, for example. In the base 2 system, we start with units. That's the one computers use. There are only 2 leaves. And what are the leaves? We said they are 0 and 1. So let's assume a community is using base 2 system to actually count or record the number of people in their community. They start with 0, they start with 1. There's 1 person in the community. I just added 0 here. Okay, if there's nobody in the community, that will indicate that nobody, that is a desert or something. But let's assume the highest is for now, there's only 1 person in the community. If 1 person joins, there are now 2 people in this community, but they cannot write 2 here. And if you think about it carefully, they can't write 2. Why? Because there is no 2 under the leaves, so they don't even know what this 2 is. If we were to be using a base 2 system, we won't even know what this is. What we know is we can only work with 0 and 1. So what that implies is, I'm going to leave this like this, is that since there are 2 people, they have to create another placeholder for 2. They'll create another placeholder for 2. So if there are 2 people in the community now, what do? They will write 1 under these 2. That is, there are 1 2's, and they will leave this one as 0. So anytime somebody sees the number written like this, they will know that, oh, they moved from one placeholder to another placeholder. They kept 1 here, meaning there are now 2 people. That's 1 2's, and 1 plus 1, of course, is 2. So this is equal to 2, actually. That's 2 people in the base 2 system. That's the value of the number 1 and 0. If there is 1 more person that comes into the community, that means there are 3 people in the community. They cannot write 3, of course. They can't write 3 because there is no leaf for 3. So what do? They will leave this as 1 under 2's, and 1 under the unit place as well. So this is 1 1 1 1 1 2's and 1 1. Since this unit is representing just 1 1 will be 3. Something like this. Now, if 1 more person joins, let me just go ahead just one bit. If 1 more person joins, there are 4 people in the community now. there is no symbol to represent 4, similar to the way a banana does not work here. There's no symbol to represent 4. If one more person joins, what did they do? They have to create another place value for 4, and we'll call that false, the false place. So you can only create a placeholder when you need it. So what do? They will keep 1 here, and this will be 0. They keep 1 here, this will be 0. So I have 0. So 1 0 0, and this will be representing 4. 1 0 0 will represent 4. So if they keep increasing, and let's say this is 1, this is all. Let me clean this. Let's assume we have a case whereby they have filled this 3 placeholder. This is 1. They fill the 3 placeholder with 1 1 1, because they don't have any other symbol apart from 1 and 0. So 1 represents that there is something, 0 represents that there is nothing. So when you see, if you are in this community and you see 1 1 1, 3 placeholders filled with 1, and you know of course that the placeholder value is increasing as you go like this. It's increasing as you go left, from the right to the left. The first one here is having just 1. The second here is having 2. It's having 2. So 1 under 2 means 2. So the third one, that is to the far left, is having 4. So 1 under 4 means 4. So this will be 4 plus 2 plus 1, which gives us 7. Good, it's filled. Now let's assume there are 7 people in my community until one day one person joins again. There are now 8 people in my community, and we use a base 2 system. What do we do in this case? There is no symbol to represent 8 that will say, okay, cool, we're going to draw a staff or a crown. And anywhere everybody see the crown when we are writing numbers, we're like, oh, that is 8. Oh, 8 people are there, or 8 numbers, or 8 fruit, or 8 something. You get? What do? They have to create another placeholder for 8. They'll create another placeholder entirely for 8. So they'll say this is 8. 8. So it's a group of 8. It's like counting in 8s, counting in 4s, counting in 2s, counting in 1s. So in this case, they will keep 1 here. And what did they do? They make this 0, 0, 0, and 0. Make this 0, 0, and 0. So what this implies, anytime somebody sees this in that combination, this is 8. 0 unit, 0 0. Anytime they see 0, there's nothing there. So what they will focus on is this, that this is 1, and it's under the 4th placeholder. And the 4th placeholder, they will look at the value of that, it's 8. So there are 2 ways to look at this conceptually now, because like I said, the reason for showing you this is so that we can find or find that observation or that noticeable significance in this conceptual thinking. Because when we find that significance, it will be what we would have definitely understood it better, and would have gotten a method, an easy method that we'll be familiar with, that we'll use to solve the questions above. So what do we notice now on your own? If you look at the placeholders themselves, and tell me what you notice. Is there a relationship? Is there a significance? Is there a way you can relate this to this, that is the base 10 system to the base 2 system? Of course, yes. And what is relationship? The first from the far right now, remember we count from right to left. The first placeholder is always units. Is unit here, is unit here. The first holder is always unit. The first placeholder is always unit, that is it. The second placeholder is always the base itself. In this case, you can see it's base 10. In this case, you can see it's base 10. So the second placeholder is 10. In this case, it's base 2. So the second placeholder is 2. The third placeholder now, that is counting from right, is the product of the base times itself. So in this case, since the base is 10, I'll say 10 times 10 will give me 100. And that is the 100 you are seeing here. In this case, since the base is 2, I'll say 2 times 2 will give me 4. And that is the 4s that we are seeing here. In this case, since we went one step further, I can use that one to explain. The next placeholder after the top, which is the 4th placeholder counting from right to left, is what? Is the product of the placeholder before it times the base. So that is 2 times 4, which is 8. 2 times 4, which is 8. That is 8 we are seeing here. So in this case, remember we used this one as an example before. So let me just bring it here. The next placeholder after 100, we already know it, but let's assume we did not know it. Comparing it to what we have here, it's very evident that it's going to be what? The placeholder coming before it, which is 100. We don't know what will come next, but the placeholder coming before it by the base. So that will be 100 times 10, which is going to be 1000, and that is the 1000 we have here. So it's very easy working with our own number base. We do it almost unconsciously. If they wake you up from sleep, you can even do it. But the understanding of the concept is what will help you to deal with other bases. Let's assume one day everybody just wake up and they said, oh, we're not going to be using base 10 system again, we're going to be counting in another base. What do we do? Good. So the second thing I'm going to explain before we go and solve this question is that this, we are very correct if we observe what I observed. 2 4 8, like 2 times 1 2, 2 times 2 4, 2 times not 2 times 3, it's more like 2 times 1 2, 2 times 2 4, 2 times 4 8, 2 times 8 16. That's how we keep going. But in this case we have 10 times 1 10, 10 times 10 100, 10 times 10 times 10 1000. So it's more like indices. If we have done indices before, we can see that this is more like units is 1. A unit is 1, and that 1 can be written as 2 raised to the power of 0. This is 2 in one place, which can be written as 2 raised to the power of 1. This is 2 in two places. That's 2 times 2. Remember we said you multiply the placeholder by itself. That's 2 raised to the power of 2. This is 2 in 3 places. That's 2 raised to the power of 3. So we are using the idea of indices now. Since we are multiplying a number by itself now, we're just repeating, we're just increasing the number of times we multiply by itself. In this case, this is unit. Unit is 1, which is 10 raised to the power of 0, because anything raised to the power of 0 is 1. 10 raised to the power of 0. Let me clean this so that I'll have space to write it in indices form. Then this is 10 in one place. In one place, that's one group of 10s. 10 raised to the power of 1. Hundreds, 2 group of 10s. Remember we said as you move from right to left, the next placeholder will be the base times itself, because we have filled up that placeholder, so we have to go one step further. That is 10 in 2 places, which is 10 raised to the power of 2. Going further, we have 10 in 3 places. That is, I did it up. Okay, I've cleaned it. That's going to be what? The next one is going to be 10 raised to the power of 3. So you can see that we are just, as we move forward now, what do we observe? The value of each number is increasing in powers, but the base remains the same. In a base 2 system, it's still 2, 2, 2, but the powers move from 0 to 1 to 2 to 3. So we just count our natural numbers like that, our integers including 0. So we start from 0 to 1 to 2, but the 10 remains the same. The base remains. So in a base 8 system, for instance, let's go and look at the one that we want to solve now. In a base 8 system, for instance, if we were to write the values 4 and 5 and 7, base 8, if we were to write the values of these numbers, what would their values be? In this case, it's not going to be 2, it's not going to be 10, it's going to be 8. But this first one will be 8 raised to the power of 0. The second one will be 8 raised to the power of 1. The third one will be 8 raised to the power of 2. So if we expand this now, the expansion is more like to multiply. We'll say this is 4 times 8 raised to the power of 2 plus this 5 times 8 raised to the power of 1 plus 7 times 8 raised to the power of 0. Once you expand this, if you use your calculator, this is 8 squared, which is 8 in 2 places. 8 times 8 is 64. 4 times 64, put it in brackets, plus 5 times 8 in brackets, plus 7 times 1. So when you work this out with your calculator, what do we have? 64 times 4 will give us 256. 256 plus 8 times 5, or 5 times 8 is 40, plus 7 times 1 is 7. If you add all this, what do we have? This is 296. 296 plus 7 will give us 303. So this is 303 in base 10, and this is our answer for this. So we'll do this, then the last one will be like an assignment. 10110 base 2 to base 10. Before we just need to know the values of each of these digits. And how do we know the values? The first one here is good. This is 2 raised to the power of 0. The next one is 2 raised to the power of 1. The next one is 2 raised to the power of 2. We have 2 raised to the power of 3. And this is 2 raised to the power of 4. Then we write in expanded form. So in expanded form now, we have 1 times 2 raised to the power of 4, put it in brackets, plus 0 times 2 raised to the power of 3. Of course, we know anything multiplied by 0 just means there's nothing there, so we can neglect it. If you neglect it, there's no problem. You can just skip it. Plus 1 times 2 raised to the power of 2 whole, plus 1 times 2 raised to the power of 1, plus 0 times 2 raised to the power of 0. So we're going to focus on the ones that have 1, because in a base 2 system, 0 means nothing. In fact, in all bases, 0 means nothing. We know. It's like somebody saying, I have 1,000, and somebody say I have 1,005 naira. You see, the only difference is that in the units place, there's 5 compared to where there's 0. So 0 just means nothing. What matters is the 1,000 itself, the one that's on the thousands place. Okay, so expanding this now, 1 times 2 raised to the power of 16. So I have 1 times 16 plus I won't focus on this, I'll follow this. 1 times 2 raised to the power of 2 is 4. That's 2 in 2 places. 1 times 4 plus 2 raised to the power of 1 is 2 in 1 place, is 2. 1 times 2. So this gives me what? If I simplify this, what do I have? I have 16 plus 4 plus 2. And if I add this up, 16 plus 4 is 20, plus 2 is 22. So this is my final answer. That is the answer in base 10, 22. So we're going to solve this one as an assignment. 14B3 in base 16. To solve, you leave an answer in the comment section. If you have any confusion in the number base, perhaps the concept I explained here, which is very interesting and makes it easier for us to even solve this without even writing, like in our head, just looking at the number. I believe when you look at the number now, you should understand the concept behind it, even though it's in other bases, that each number differs in values as you go from the right to the left. Thank you for watching.